The second example that we will be considering is that of an infinite line of charge that carries a uniform charge density lambda distributed over its surface, its length. That is, it's illustrated here. So the charge is distributed over a line, and this line is infinite, and we are requested to find the electric field at some distance r is arbitrary, from the charge, from the line, sorry. Now, just before I proceed, I'd just like to make a comment regarding this infinite length, because we will be talking about an infinite charge, infinite line, then we will be talking about an infinite cylinder, an infinite plane of charge. All of these are infinite quantities. Of course, in real life, we don't have these infinite lines of charge or infinite planes and so on. These are idealizations. These are idealized models. However, the result that we derive for the electric field using these infinite models is valid in real life when we are at distances from, for example, the wire that are small in comparison to its length, and we are away from the ends of that wire. Okay? So we will continue using these idealized models, but we have to keep in mind that these are actually idealized models, and their applicability in real life situations where we have finite distribution is when we are at small distances, small in comparison to the dimensions of the charge distribution, and we are away from the edges. So we apply the same strategy that we have learned about Gauss law in trying to find the electric field here. We will use the Gauss law. So we have to pick out what is the right Gaussian surface. Now, to find out what is the right Gaussian surface, we have to know something about the electric field of this infinite line of charge. Now consider a given R here and a few R here. What you can say about the electric field in here? Now, the first thing that you can say about the electric field here is that the electric field doesn't have only one component which is away from the line of charge. That the electric field here is just in this direction. There are no component neither in this direction, nor in this direction, nor out of the page. Okay? Why is this? Well, it is easy, I think, to understand, because when you are talking about an infinite line, every point on an infinite line is a middle point, because it's infinite. So you can appreciate this. So at a middle point, the electric field that is here is contributed from dq's. If you think of that, this line is divided into dq's that go to infinity from this side and from this side. Each dq here will contribute a field. For example, if this were my if you choose a dq here, it will contribute a field in this direction. There is a mirror image that will contribute a field in this direction. The sum of these two fields, when you add up these two, they will cancel the component that is other than this component, and these components will add up. Now this applies to contribution coming from all dq's to this point, and therefore the electric field at this point will be only in this direction. And this applies to each point, because each point here can be considered as being above a middle point, because the line is infinite. Okay? So this is why we can conclude, due to the symmetry here is what? The charge is uniformly distributed over the line, and the line is infinite. The symmetry comes from this. And if you move along the line, the at a given distance from R, the electric field will not change. Why? Because again, it's infinite. When you move horizontally this way and you look, you are above a middle point. So you see the same charge environment both ways. And so the electric field cannot change as you move in this direction. Not only this, if you rotate about the line, as long as you keep this distance r the same, then in this case you will also see the same charge environment. Okay, because this is a line of charge and the charge is distributed over this line. Okay, so if you take a circle, have radius r, and rotate about the line, then you will see the same charge environment all the time. So I get two things about the electric field. If I choose a cylinder of finite length L, then at the surface of this cylinder, the magnitude of the electric field is constant, because at all points on this cylinder, from all points on the cylinder, when I look at the line, I will see the same charge environment because it's infinite. And each point here is above a point which is at the center. And they are all at the same distance. Okay? So on this spherical surface, on this, cylindrical curved surface of the cylinder, the electric field is uniform. And we have seen that it has a component that is away from the wire. So the electric field at all points here is normal to the surface of the cylinder. So we have fulfilled the two. So this cylinder, curved surface of the cylinder, fulfills for me the two requirements of a Gaussian surface. First, the field is constant. The second, the field is always perpendicular to dA, because what's dA here? It's an area element which is a vector, and it's normal to the surface. So since the field is normal to the surface, it's always parallel to dA. So, and this applies for all dAs. And therefore, the angle between E and dA in this case is 0 all the time. Now, this is true for the curved part of the surface, but it's not true for the upper base and the lower base. On the upper base here, the electric field, I cannot say that the electric field will be constant, because here you are at different r, so the magnitude of the electric field might vary in this case as r increases. But what I know about it is that the electric field is always along r, so it's always in this direction. And since on this upper, and the same applies for the lower, the dA vector is always normal to that surface, then the angle between the electric field at the surface and dA is always pi over 2. And so cosine that angle is 0. And so in the Gaussian integral, the E dot dA expression for the upper and lower bases will give you 0 all the time. So it doesn't contribute to the flux. The meaning of this is that there is no flux of the electric field lines through the upper and lower base, which is only normal because the electric field lines are, the electric field is going outwards, radially outward, and so the electric field lines here will be what? Will be just parallel to this surface. Okay? So they are not penetrating these upper and lower bases. Now we do the analysis after we have given the introduction about the Gaussian surface and the symmetries. And so this is my line of charge. And this is my Gaussian surface with length L, and the electric field at the surface here, as I know, if I take a dA here, this is A and this is dA. Now I apply Gauss law. I know that the charge density, uniform charge density is sigma. Now apply Gauss law to this surface. So this is my surface S, and it's composed of three parts. Call this part, let me use another color. Call this part S1, this S2, and this S3. Now I know that S2 is equal S3, the area of S2 is equal to S3. Okay? And let me call this, for example, S prime. Now I apply my Gaussian integral, which is the left-hand side of Gauss law. I say that E dot dA, this is my Gauss law, and this should be equal Qn divided by epsilon naught. Now I start with the left-hand side and try to take out E outside the integral, and then I will worry about the right-hand side. Now, this is a surface integral, and it's about, it's evaluated over the whole surface. However, this surface is now has like three portions. One portion is the cylindrical surface, the curved surface. The other are the top and lower base. So I can split this into integral over S1, this surface, E dot dA, plus integral over ES2 plus integral over S3 E dot dA. So this is this integral reduces to the integral over the closed surface reduces to three integrals over three open surfaces, because each of these surfaces now is an open surface. Now I look at this E and dA here. Now any dA here, for example, in T on S2, as you can see, any dA is actually normal. Now the electric field, as we have argued at the beginning, the electric field is always has no component other than the component that is perpendicular to the line. So over this surface, the electric field is always tangential to the surface. So it's perpendicular to dA. So the angle between dA and the electric field is always pi over 2. Okay? So this surface is equal E dA cosine pi over 2, which is 0. The same applies here. This is also 0. So this integral reduces to an integral over S1 E dot dA. So the integral over the closed Gaussian surface reduces to an integral over the open of one single surface, which is the curved or the cylindrical part of the surface. Now, on this surface, E and dA are parallel all the way. E is constant, as I have seen, and so E dot d, this reduces to integral over E dA over S1. E is uniform, I take it outside, so it becomes E integral over dA. And what is dA in this case? dA is nothing but the area of the cylindrical surface. Now, this cylindrical surface, of course, has radius r. Why? Because, I want to find the electric field at a distance r, and so the surface should pass through this point r, so it has a radius r. So what is the area of this cylindrical surface? Well, if you unfold it, it is a rectangle which is its area is length L multiplied by the circumference of the circle here, which is 2 pi r. Therefore, this expression is equal to 2 pi r, so I get E multiplied by 2 pi r is equal Q enclosed over epsilon naught. Now I want to work out what is Q enclosed, and then I have an L here, sorry, 2 pi r L, and this is equal Q enclosed over epsilon naught. I need to work what is Q enclosed. What's Q enclosed? Q enclosed is the charge of the line that is enclosed within the surface. In other words, it is the charge on a portion of the line which has length L. And since the charge density, the linear charge density, is lambda, then this charge is equal lambda multiplied by L. So this is equal lambda L divided by epsilon naught. Therefore, this L cancels this L, and you get E in this case is equal lambda over 2 pi r epsilon naught. This is the magnitude of the electric field. And if you want to write it as a vector, you write it lambda over 2 pi epsilon naught r hat. Now r hat is a unit vector that goes from, if you want to find, for example, the electric field here, then this is r hat here. It is a unit vector that goes from the line to the point where you want to find the electric field. Okay, so it's radially outward from the line, and this is your electric field vector. This is the magnitude of that electric field. To check it, one check, as we have always said, is the check of dimensions. The electric field should be like k multiplied by, and dimension-wise should be k multiplied by Coulomb divided by r squared. No, 1 over 2 pi epsilon naught is roughly 2k. So, okay, k is there. I must have Coulomb per meter square. This is Coulomb per meter, and I have meter, so it's Coulomb per meter square, so it's okay. So it's okay. The electric field is okay dimensionally. Now, as you note here, the electric field drops as 1 over r. So as you go away from the line, the electric field becomes smaller, and this is the electric field of an infinite line of charge. Okay? At the same distance, it is uniform, and it is always perpendicular to the line of charge.